Welcome, everyone. It's 11 o'clock. We're going to get started. We are talking today about laser plastic welding, the fundamentals and the applications that you can expect. I'm Jason Dornbos. I'm a sales manager. With me in the room over there is
Nick Flesher. I'm Director of Innovation and Development at Axle.
As we go through, the chat is your tool to communicate with us, and this will be such a better experience if people are typing things into the chat. I appreciate everybody who has sent us their favorite emoji. If you haven't had a chance to do that, go ahead and drop your favorite emoji into the chat, and we will get started because we have a lot to cover today. But if you have questions along the way, please type them in. We will do our best to address them in the moment. We don't like to save questions for the end because
it's less interesting.
Yeah, and you have the question right now. So how are you going to learn anything else until that question gets answered? That's what I think. All right, let's get started. First off, question for you guys. Why did you sign up for this webinar? What are you hoping to get out of it? Do you just like our webinars? Do you like laser welding? Never heard of laser welding? Let us know why you signed up for this webinar.
Jason, I wonder if they realize we're going to wait until we get that.
Maybe, yeah. Hopefully people start typing and put something in there. Yeah. Never heard of laser welding. Thank you for being brutally honest. The next question, or there's going to be a question later on that you're going to love. General info. Interested in applications. Great. To learn when laser welding would work over hot plate. Ooh, that's a good one. A volcano. General knowledge. Interested in the technology, learn more about it. Considering laser welding, currently struggling with ultrasonic welding. That's never something we've heard before.
Probably the most common theme we get. We'll address that later.
Yep. Learn about new tech. My company is starting to look into this for a project. That's great. Awesome. Keep them flowing. We asked you when you registered if there was anything specific you hope to learn about laser welding. And a few of the answers we got were when and why to use laser welding, kind of pros and cons, how to laser weld absorbent to absorbent parts. And if you don't know what absorbent means, we'll get into that. Laser welding speed versus ultrasonic welding, how to design the weld profile, and material compatibility. And there's lots of other questions, but this is these were some of the main themes that we saw in a lot of those responses. So we'll do our best to address all of these things as we get through it. Real quick, we're going to do an introduction of Axle. Axle solves complex plastic manufacturing challenges. If we zoom into the square portion of our logo, there's a little chart here. On the left-hand side, we have plastic welding expertise. On the right-hand side, we have custom automation expertise. Companies that are experts in plastic welding often don't do very well with custom solutions. On the right-hand side, custom machine builders often lack plastic welding expertise. This is where Axle comes in. We are the best of both. We have plastic welding expertise and custom automation expertise. So you get a configurable plastic welding solution that's optimized for performance. We have three main areas that we can help you with: engineering services, plastic assembly technology, and custom automation. These are kind of how those all break down. Under engineering services, we can help you with development and the design and feasibility testing, all those things that that you have to work through before you start launching a production line. We can help you with that. We have a whole bunch of plastic assembly technologies. We're going to focus, of course, on laser welding. And then we can do custom automation. So not only do we provide plastic assembly technology, but we can build you the whole solution in a custom automation machine, both fully auto, semi-auto, standalone machines. And if you want to integrate our technology into your own machine or have somebody do that for you, we offer our technologies as integration packages. Are there any questions so far from the team? No? Chat's good?
Chat's great. Okay. We got a question that I highlighted that we're going to definitely address, but I'd say keep going.
Awesome. Axle aims to partner with you throughout your project lifecycle. Yes, you will get the slides afterwards. Scott?
Great question, Scott.
Development, validation, equipment, production, post-production. Is this how your project life cycle goes? You have development, validation. We can help you with manufacturing concept ideas and 3D printed samples. When validation, we can help you with prototype welding and testing, along with pre-production part builds when equipment's not quite ready yet. We can help you with equipment, of course. That's the main bread and butter of what we provide, is the equipment that actually performs the work to make your plastic assembly a reality. And then in production, we help you install it. We can help you with preventative maintenance. You can get spare parts. We can help you with repairs, troubleshooting. And then at the end, when these things are going into the life of service, or they need to just be retrofitted maybe for new tooling, we can help you with all of those things. On a scale from 1 to 10, and hopefully I'm just going to see a flood of numbers coming into the chat, how much experience do you have with laser welding? 1 would be, what is laser welding? 10 is, I could teach this webinar. 1, 5, 1, 1, 1, 1. Wow, lots of ones. Okay, great.
I see a 10. I'm nervous.
Ooh, okay.
I saw a 10.
All right. 5, 4, 6, lots of middle of the roads. Great. This is good stuff, guys. Well, hopefully we can cover the spectrum of starting points. You know, it's always hard to jump into something deep when you're new, and it's hard to listen to basic stuff when you're experienced, but we'll do our best to address all of it. With that, we'll jump in.
Yeah, let me just pause too and say, Jason kind of said we're going to try to tailor this webinar. You know, we'd like to do a very live, interactive, as you've seen. We're going to get into the details now. Thanks for listening to who Xtool is. That's really important, so you can kind of grasp our approach to things, and our applications lab through that development process is key in laser plastic welding for a lot of the reasons that, you know, a lot of folks are saying 1s, 2s, not very familiar. We have a whole team set up to help you with that. On the flip side, I saw a 10. We do have a couple other webinars that we might point you to at the end of this webinar that might be a little bit more in depth, or a little more comprehensive. So let's talk about the process. What is this thing called laser plastic welding? First off, it's been around for quite a while, but I think has really gained in popularity, I would say, in the last 5 to 10 years. Let's talk through the process just to get a basic understanding. Clamping is really key. You got to have intimate contact, is the phrase that we use, of 2 components that you need to weld. You have to be able to heat it with a laser, and you got to cool it. Cooling is the curing process. We find that it's really important to maintain pressure. We're going to talk about process parameters, but just at a base level, that's what the laser welding process is. There's a slight variation of through transmission, which is what this is showing, but essentially, you still got to heat, you still got to clamp, you still have to cool.
Oh, you got to take control.
I think I got it.
No, you're not. Hold on, go to hit that button. There you go.
Pause 1 second. All right, thank you. All right, so here we go. What's important when you're trying to laser plastic weld? You understand the process just from that brief summary. I mentioned intimate contact. We find that actually a lot of customers that may have experience with laser plastic welding in the past might actually struggle with this intimate contact. The correct tooling and force is really important when it comes to laser plastic welding. The IR transmissivity and absorptivity. What are these 2 words? Essentially, you have to get enough energy through that first layer to absorb into the lower layer. And so we'll talk through materials just a little bit later. We won't go too deep in this webinar about that, but that is crucial. And there's certain things that affect both transmissivity and absorptivity, but both of those things are key when it comes to laser plastic welding. And then third, and we'll show a compatibility chart later, is you have to have good compatible materials. This is true for any kind of welding that you're doing. If it's vibe or ultrasonic or hot plate or infrared with other methodologies, you need to have good compatible materials.
If they aren't compatible, they won't weld.
That's right. So those are just high-level conceptual. We're going to show a couple of videos here so you can kind of see the process. Hopefully the video is not too choppy. We can't really talk through these videos because it doesn't come through exactly, but we'll show 2 videos right now just so you guys can actually see it in a production type setting. Okay, so what you guys just observed there is the parts were loaded, the clamp came down, the laser turns on, starts applying that laser energy through the transmissive into the absorptive part. You saw a slight hold, then you saw the part tilt up. One key thing that Jason talked about is how we do focus on custom solutions. And so this particular customer, we eliminated another machine, a laser marking machine downstream. We get this question a lot when we show this video. Unfortunately, you can't use the same laser to laser plastic weld as you do to laser mark. They're doing kind of totally different things. One is high power, a little larger beam spot. The other is lower power and a little more finite. So I saw a question, Jason. Do you want to pause for a minute?
It was just about materials, and I quickly addressed it, but here's another one. What flatness profile tolerance is required in the plastic shells? How flat do they have to be?
Yeah, I think it's a really tough question to answer, and I'll tell you why. These particular parts are approximately 6 inches in length. This customer needed the throughput, so we did a 2-up weld. We have different ways we do that. And I would say it's this kind of... we don't have firm calculations for this because it depends on how pliable your parts might be. Sometimes we're shimming tools that might be 3, 4, 5 thou, up to 10 thousandths of an inch. And so we can do a lot of things with force to get parts flat, to get that intimate contact. Great question. I think there's not a hard and fast rule on that necessarily.
You answered the second question, and then the third question so far is, how is that inner template held? It was actually attached to a glass plate. And then there's a glass, I don't know, was it inch thick glass?
Yeah, approximately an inch thick.
And then we bolt aluminum shaped tooling because of the top of this part not being perfectly flat.
Yep, that's right. And we to provide intimate contact, mostly we're trying to encapsulate the outer and the inner portion of the weld. There are times when we can just capture the inner portion. You need to be cautious of cantilevering when you do that. You can laser, the laser does go through the glass, so I just saw that. You can laser weld through that. You'll notice there's not, in this particular example, and most, I would say 95% or more, laser plastic welding, there's no smoke, there's no particulate, so it's a very clean. You'll see that, some examples of that here in a moment. But great question so far. I'm going to show another video. This is more of a custom application. No problem, Randy. More of a custom application. We had 2 laser plastic welding systems on this one. You're going to see it dry cycling. It's not got the parts present. We're sort of, this is early production, and so just to respect that customer, we don't have the parts shown here, but you'll at least see kind of the form factor. This is running one operator to weld 2 different welds, leak checking and laser marking all in one system. Extol provided all of this. Great question. 2 welders to reduce cycle time. In this case, actually, we were hitting the part in 2 different areas for the 2 welders. In the one welder that had the 2 beams, it was exactly that. It was to reduce cycle time. We show some numbers on that a little bit later. So speed is another reason you choose laser plastic welding. But as you can kind of see with these 2 examples, it gives sort of a mechanical... are the parts invisible? Sorry, that one distracted me a bit. We actually omitted the parts from that line in this dry cycling because of confidentiality.
And actually, in the laser shot, all you'd be able to see is the very, very edge where the weld is on that part. So you can't, there's mostly tooling covering the parts. That's why you can't really see them.
Yep. I saw two questions pop through.
How easy complex is it to teach the routine of the laser?
Really straightforward. The software, you upload the CAD, the 2D CAD of the weld profile, and then you can make adjustments pretty easily with the software.
Can plastic caps be welded to each end of a hollow plastic tube and be hermetically sealed?
Hermetically sealed parts are most common in laser. I am going to show a stitch weld. Actually, I'm not going to show a stitch weld application. It shouldn't be a problem. I think we would need some more information to answer that one. Let's park on that one. We've got record of that question. I'm going to keep moving.
Other part testing methods.
Yeah, let me pause on this one for a moment. So with laser to plastic welding, because of the inherent transmissive properties, there are many cases where you can do a visual inspection of the weld in line. And so we actually had an application where most oftentimes we'll use weld depth as a control parameter. How deep was that weld and over what amount of time? And then you sort of overlay those two parameters to give you good quality parameters. And this particular application couldn't do that. It was very compressive. And so we said we have to do a visual inspection. And we just, with the correct wavelength and the correct filters, used a typical, it was a Keyent system on that particular application, but you can use any camera. I'm going to keep moving here. Let's talk about wavelengths, okay? It's infrared energy, so it's a little strange, and we'll talk about electromagnetic waves again a little bit later, but these are the three methods that we see in production and in our application space for laser wavelengths. 1 micron is commonly referred to in the industry. We use 980 nanometers. Some people use some companies use 940. Some use 1060, 1040, I believe. And this is kind of a visual of what that transmissive welding process looks like. You'll notice it's very intentional with, we call a heat affected zone. That red line is really, really precise. Very, very small, very finite. Clear to clear, we can use a different wavelength. We can use 2 micron, and it doesn't have to be optically clear. It can be transmissive. There's different material constraint properties that help with this. 1940 is the wavelength of that. And then there's this thing called direct laser welding. We've done it with both wavelengths that I've mentioned here, and you're essentially heating both parts and pressing them together. So as you hear these three terms in laser plastic welding, that's kind of what these things mean. There's this quirky thing in laser plastic welding with mirrors. Not all mirrors are created equal. And essentially what we're doing is we have a fixed scanner or fixed like optics and scanner package where we're bending the laser around the profile that you want to weld. And when you have undercuts, think like fittings with 90s on them, or you want to radially weld it, but it might be an odd shape, like this one to the right is kind of an odd and unique shape. We optically engineer those mirrors to bend the light around that path. And what you get is you can move the laser beam at up to 3,000 millimeters per second, and therefore get a really uniform heat. This particular application on the left, it almost doesn't even look like a weld joint. There's no particulate flash. It just looks like a wetted out piece of plastic, almost like an overmold. So here's a custom example just to kind of get your creative juices flowing when you think about direct laser. And again, we have another example in addition to this one. But in this particular case, the customer came to us with a really tough challenge, and we ended up applying mirrors. They were used to rotating the parts. And so we rotated the parts while we applied the laser energy to the inside of the part. We used 2 micron to do it. It was better at penetrating the part and going a little deeper, and they wanted that deeper heat affected zone. They wanted infrared measurements, so we ended up using kind of off-the-shelf temperature pyrometers or IR temperature sensors, and they wanted quick change tooling. So kind of a unique application where we helped this customer with a really specific request. I'm going to talk about the types of laser plastic welding. I would say that 90+% of what we do is quasi-simultaneous. And when you hear that phrase, what that means is many passes really fast, trying to get the temperature of the weld surface up as fast as possible, as uniformly as possible, and then we simultaneously displace the material. Contour welding is one continuous path. Sometimes we see the applications can do both things just as well. Sometimes you really need that quasi-simultaneous to make sure that you got uniform collapse on the part. Line beam is kind of a specific application where we're basically using just the optics, not the scanner, to paint the width of the laser beam across the parts. And then lastly, masking is used, I would say, fairly rarely, but it's essentially when you need really precise energy distribution with less than 0.7 millimeters of width. All right, that example I referred to earlier, here's a video of direct laser welding. And again, we've got these parts, at least they're visual here, but they're kind of blurred out so you can kind of see what's happening here. So I want to pause. This material was a glass-filled nylon. And this particular customer was thinking ultrasonics. But if you're familiar with ultrasonics, you have to be very careful about what's called far-field welding, essentially having the energy source or the horn back up from the weld rib. And got pretty far down the project path, couldn't get good welded parts from multiple ultrasonic suppliers, and couldn't make it transmissive, and so we pivoted to direct laser welding for this. You saw the speed. That's obviously a little longer than ultrasonic welding in this case. There are cases when it's not longer, but those are some details around this application that really was I think a big win for the customer.
Okay, so can you address the smoke?
I should have done that proactively. Okay, so this is the case where smoke shows up in laser welding and would be for any IR welding. It was a single laser on this particular one. So we have to, there's no way, smokes in laser plastic welding, especially with black nylon parts, is oxidation that's happening. You're essentially just burning the part, and it happens without really much control. We evacuate it. In this case, this was actually in the prototype machine. We did do a production machine, and we evacuated it really, really quickly. That question that we just had asked, is it similar to IR welding? In this case, yes. We have InfraGuide as a tool that I encourage you to check our website out. It's sort of a different tool in the toolbox for laser for black nylons and other sorts of sticky materials, or where ultrasonic doesn't work. But yeah, that's not typical for laser plastic welding. It only shows up in direct laser plastic welding. If you have smoke through transmission, you have a process problem. Typically force is what we see. If a customer comes to us and can't process out smoke, maybe from a previous supplier's machine, that's typically the problem.
And the smoke is from, it's the fact that the joint is exposed to the air, right?
Correct.
Okay.
Yep, that's right.
Another question was, why would we do this with laser instead of hot plate? And that's kind of a general question because nylon does not behave very well with hot plate. When you have to take a nylon or a PBT, there are certain materials that if you contact weld them, meaning you're touching the plastic to a hot piece of metal in order to put energy into it, they stick like crazy, and it's really messy, and it's not a good long-term solution for production. That's why we have non-contact welding technologies like laser, infra welding, and other types.
Yep. I want to say thanks to everybody's questions. This is fantastic. We're going to keep moving. We've got about 15 more slides. I just want to touch briefly on the electromagnetic spectrum. Everyone brush off their physics books from high school. If you kind of remember what that is, you've got gamma waves all the way down at the bottom, radio waves that are all around us. And what we're focused on is the infrared spectrum, just above that visible light. And so you've got near IR, long wavelength IR. If you've done any infrared welding with quartz tubes or hot plate hovering, which is a common methodology that we use, it's all within this sort of spectrum. Each plastic likes a different wavelength, frankly. We're not going to go into that too much right now, but just to kind of bring from the physics side of things, what we're doing at 1 micron at the 940 wavelength and then 2000 or 2 micron on the upper length. That's what we're doing that's what we're using within the infrared wavelength spectrum. So most common question we get, and we've got a few slides to cover it. When do you use laser plastic welding over insert your welding method of choice? Ultrasonic is probably the most common that we get because either it's gone sideways a little bit, or maybe there's some particulate, or maybe once that melt starts to happen, it goes too quickly. The number one, and vibration is a common that we see. The number one reason is it's clean. There's no particulate. We've shown some examples already. This is actually about 1.5 inch plaque. It's not our best image, but I think it does show really well. The flash is essentially nothing. There's always flash, but it's oftentimes visually appealing. It's like it's a purposeful melt is what I would say. You don't get any excess heat. In this particular example, you can see there's really not much heat effective zone past that little small roll of flash. So clean, clean is number one. Assuming fume extraction is required. What is that question?
Do we also require additional chillers for heat absorption?
That's one great thing about laser plastic welding. There is virtually no heat absorption if the laser is going where it's supposed to go. So it's a key process parameter that you're watching. But this particular image I'm showing right now, is a great example of that. If your part's smaller and you're not putting much energy into it, there's just no excess heat. And so you don't need chillers. Sometimes we use a little bit of air, with an air knife, but even that's not necessary with properly processed and designed and tooled laser plastic welding. So first and foremost, cleanliness. Second, precision. It doesn't have to be a small part to need precise welding, right? Like you can have a larger part and just need to make sure that heat is going where it's supposed to go. This particular application, I think we were collapsing 0.1 millimeter that you see on the screen right now. 100 watts. I think actually it was even less than that, and it was 1 second of energy on time. We can accomplish laser beam spot sizes between 0.7 and 4 millimeters. So precision is number two. If you need precision, that's really important. And then three, before we backtrack to the questions, is speed. As I said, lots of different welding methodologies out there. Ultrasonic can be the fastest, but this particular part that you saw the video of that we're not showing is approximately 12 inches long. And so to weld a part that fast, maybe you go with vibration. That's a filter housing, a filter element, and a filter housing application. And so we need it to be clean. They had to have it fast. Laser on time of 5.1 seconds. Great question, Jeff. Do you need energy directors? You do not need energy directors. We're actually going to show joint. You know what? Actually, it's next. Let's go ahead and advance to it. But keep these three words in your mind. If you're thinking laser plastic welding, that it's clean, that it's precise, and that it's fast. And those are real time, right? Like 5.1 seconds for a part that big is it's obviously a unique application where we were applying 1,000 watts of power to this part during that weld process to get that. But that was crucial to the customer. And we don't have to do that typically. It's usually in the 200, 300, 400 watt range. Let's talk through, we got a couple slides to show ideas for joint designs. I'll say right away, if you've got a specific application, you want to look at CAD. We've got apps engineers at the ready to do that at no charge. But just to get you kind of used to what we like to see or what we typically see, T-joints, probably the most common. I think Jeff, asked about energy director. You don't need an energy director, but it's nice to have a sacrificial rib, whether it's a lap joint like this or a T-joint. But you're not using that to generate the energy like ultrasonics. If you're familiar with ultrasonics, that's how you start the energy transfer. You don't require that. We see a lot of skirt T-joints, upper skirt, sacrificial T-joint. You'll notice it's a little different configuration where you've got an outer lip that's on the upper part. And then probably less common, I would say, Jason, is the upper skirt T-joint. Yeah. And these are our phrases. Everyone might have some different verbiage there. So let's show them a material compatibility chart. You can download this on our website. There was a question about does the materials need to be different. I think compatibility might have confused. That might have been a confusing phrase that I shared. But essentially, we say a strong weld should be expected if you have these materials. It doesn't have to be the same material, but it needs to be within the same family. We see a lot of PMMA, PC ABSs. Our own John Mitchell just asked if parts can be non-flat. I would say absolutely. We can hit them from the side. We can accomplish variations in 3D. Although I'll say there's a level of complexity that probably quasi-simultaneous isn't the right technology. So, the answer to that is it depends. It depends on overall footprint. We've done multiple scanners, multiple laser sources to capture sort of curved parts that have a little variation in height. You can typically hit one laser source and scanner with about 3/4 of an inch of height change, depending on part size. Jason, should we revisit those questions at all?
The process of welding looks really fast. Can both the components locate the position relative to each other before welding, radial and tangential centering?
Yeah, great question. We typically...
I was going to say you can do that with joint design or you can do it with tooling. So if I'm understanding the question correctly, how do you align your upper component to your lower component? Sometimes we have tooling to crowd the upper component relative to the lower. And then other times you can design in features in those two parts to make them self-align with each other. As long as you don't create hard stops inside of your plastic components. You don't want non-melted plastic coming up against other non-melted plastic, because then when we're pushing these parts together during welding, once you contact plastic to plastic, that's it. We can't apply any more force to the joint. And so if we haven't gotten a strong weld, we won't ever get a strong weld. So we want to make sure there's always a little bit of a gap so that when we're applying force to the weld, it is strong and we have the force going into the joint.
Jason has a question of reliability of lasers, laser welding. What preventative maintenance would be necessary or recommended? I would say our lasers, we use a domestic supplier that is a military grade laser source. And we have had machines in production for years with no issues whatsoever. I think they're technically rated for 30,000 hours. But that's not been an issue. I will say we've run into, there's a particular, I'll keep names out of the webinar here. There's a particular laser plastic welding company that has since gotten out of the business very recently, as recent as I think last month. And I have heard that there has been historically some challenges with some laser sources, reliability wise, in the 18-month range. We have not seen that with any of our production lasers whatsoever. As far as maintenance goes, you do need to keep the surfaces clean if you've got a glass clamp, which we've shown a couple examples of. But if you're dialed in, I've talked with customers that really have never cleaned it, and they don't even put it on a PM schedule.
Force. How much force?
How much force is applied? Oh man, great question. So for that really small part that was smaller than the dime that I showed, I think we're using like 50 pounds. We have used up to 6,000 pounds on really big parts. So that's the range, right? Like those are sort of the bookends. What's more common for us is 500 to 2,000 pounds. I have also, we've talked about this quite a bit from our sales organization, our apps team. We see that customers don't use enough force when it comes to laser plastic welding. It's crucial that you have those parts together because you're actually putting the heat into the lower part and it's conducting into the upper. So you got to have good contact so the heat can transfer into the upper part, right? Man, these questions are awesome.
Okay, so if you have a weld joint and there's a small gap, maybe it's a little divot from a sink mark or something like that, how much of a gap can you overcome? It's a tough one.
That's a tough one. I mean, we've seen probably the most common thing where that's come up is ejector pins on the weld surface. Try to avoid that at all costs. It can be overcome again with force. It's too tough a question for me to just sort of broadly answer. If we see gaps on 5, 6, 7, 8 inch parts that are, I'd say more than 5 thou, maybe more than 10 thou, you might have a challenge. But again, it depends on how pliable it is. If you can take that part and twist it a little bit, we can overcome that usually without issue. I see titanium oxide. That is in the advanced section, Paul. You're sorry, that's a different one. That's Mike.
Mm-hmm.
That's in the 401, not the 101 course. Mm-hmm. And I would say that it's really challenging to do white on white. In the laser plastic welding space, that's kind of the holy grail I've heard called. Can be done, but it's tricky to do. We have done a little some 2-micron stuff with that before.
Max asked if how do we assure that a burn material is fully flushed out with direct laser welding? And I would say we don't have burned material.
Yeah.
So you want to make sure that you're not overheating the surface to make it burned.
Yep, that's right. We're going to keep moving. I want to give some applications examples. We have to be careful as we do this, but we felt it important. Jason and I talked what kind of content would you folks who signed up want to see. This was an application that came through, and they had done their own best effort to design the weld rib. They didn't have a sacrificial weld rib in there. These samples that you see up top, those 4 samples, actually were not a recommended weld surface area. We ended up collapsing on that. I think it was less than 0.1 millimeter. And then this was the recommendation we gave the customer, that CAD that you see at the bottom. You can kind of see that weld rib is inboard a little bit. It's a conceal. It's not necessarily a trap. We're not enclosing it, but it allows us a little bit of collapse under a controlled situation. And it also, doing that helps reduce cycle time. It can reduce power to reduce some of the cost maybe of your machine. So kind of a cool one. Obviously, you can kind of see how small it was. I think this was a wearable device. This one, just a little video. I'm not going to get into the specifics of this because we show a little more of the part, but you're going to see a laser trace. It's called the pilot beam, so we can see where the laser's going, and then you'll see the weld. So not much time there. So this is an application that we did. We'll just say that it was some electronics, and we ended up, this was a burst test we did in our applications lab. Here's the video of that particular application. It's a little more energy in this one. I think we were capped in our lab laser and ended up going maybe a little more power in production, but still pretty quick, as you can see. We're just going to touch on material types a little bit. This is mainly to highlight that just because it's optically clear doesn't mean, optically opaque doesn't mean we can't get through it, right? If it looks like it's not transmissive, doesn't absolutely mean that you can't get the laser through it. We work with a couple compounders, a couple resin suppliers if you want help with that. This is the same part on the right and on the left with our infrared inspection system. So you can kind of see there's 2 weld ribs on this one that sort of support this. You got to make sure those materials are compatible, as we shared and as you saw from the compatibility chart. You need to make sure you've got transmissive material and definitely that absorptive. I see I've only got 5 minutes left, Jason. So
rock and roll.
Just keep going real quick. Process parameters. we just want to touch on what we control and what we watch for. This is just an example from one of our machines. Force, and we have multiple force settings. We have approach force, weld force, hold force that we're making sure that we're controlling. We typically weld on collapse. You can see the 3 weld modes to the left. How much wattage you're using, which I'll show here in a moment, of how we control that. You can see those limits, approach limits, to make sure parts are loaded correctly. Lower and high collapse limits, those are our main quality parameters, as I mentioned, if you weld to collapse. And then you can overlay time on that so after you get enough data to say, I'm within my process control for that. You can also go by number of passes, and you can adjust speed. This is kind of an interface to do power and speed. Most of this webinar is around quasi-simultaneous, and those can be anywhere from, contour welding is sort of the slower versions of that, 50 millimeters per second all the way up to 3,000. We want to make sure we highlight the equipment solution. I think a lot of people ask why Xtool for laser plastic welding, and I would say this is sort of the catchphrase that we've used. Configurable laser plastic welding solutions is where we tend to shine. You'll notice on the far left an integration package. We ended up selling that to another machine builder. We quote those packages, I would say, fairly often. This is a benchtop system. Our benchtop systems are a bit larger than some others, and that's because we're trying to put more into them. This is a pretty slick package that we have. Standalone machines, we have standard products, but also can do standalones that are customized to those. And then automated is a full turnkey solution, obviously, for this was a lights out, drawer slides for the operator to load, had inspection in it, 100% quality and offload. And then I would say another key thing around being configurable is what's the right solution once you know you've got your application nailed in our applications lab. And that is, what's your cycle time and operator requirements? What's your budget? You better be talking about that quick and early. Auxiliary functions might help you with your budget a little bit if we can put some different. We've seen compression limiters be put into laser plastic welding machines, leak check marking, things like that. Quality parameters are also really key. This particular solution on the screen, a customer came to us and they didn't really have the budget for, it was a right-hand, left-hand type application, and they had multiple parts to weld. And we put on interchangeable tools 2 welds with 1 laser source with 2 independent presses to make sure we were measuring the collapse on both of those parts. But we narrowed down the budget from 2+ machines down to 1 machine with interchangeable tools, and I think
it's a 2-position dial.
And it's a 2-position dial.
So load time goes away.
Yep. So that operator can be loading while that laser is doing its work.
All right. Can we rapid fire some questions?
Please do.
All right.
That's all we have for
Mike wants a 401 webinar.
I saw that, Mike.
So I think what we'll do, Mike, is we can reach out to you after this, and we can schedule that because what we'll probably want to do is come in and do it with your team. And there was an automotive lighting question. They talked about weld collapse. How much overlap would you want in a weld rib for an automotive lighting?
Great question. I'm going to answer a different question before I answer that question. And that is, I think a lot of times customers who are in the automotive lighting space might think in terms of big tools, simultaneous welding is, again, we didn't touch on that much, but these really big compound angles. We've seen a really big increase in applications of internal lighting components, things like bezels, side markers, projector lenses, different maybe enclosures that go within the light assembly. So I think we're really well suited to that. Better, I think, from a precision standpoint than ultrasonics. Definitely better from a particulate standpoint. So if you're in that lighting space, we would love to talk to you more about where our version might fit a little different price point, a very much different price point than what you might be used to. I knew I was going to forget the question. What was the question again?
How much overlap do you need?
Overlap. Yeah, I would say a millimeter's a lot.
Maybe half a millimeter?
Half a millimeter to 1.2 maybe. You can easily get 80 to 90% parent material strength if you're used to that phrase. That basically just means if you didn't have a weld there and pulled the part of that same thickness, can you get that same strength? And oftentimes we ask customers to design a little wider part, and you get better than parent material strength. So I would say millimeter is a pretty good rule of thumb.
There's a question about how many parts you can weld at once, and I would say it depends on how much weld length each part has.
Yes, direct laser for sure. We ended up doing 6 parts with one laser head with independent force for each one. And it was a really fast, I mean, that was, I think, a 5-second laser on time with 1 second of hold. And we were doing 6 parts, right? So less than 2 seconds per part. We really, if we do multiple parts, we really push for multiple presses. I've seen a lot of applications out there on other people's equipment where they're not allowing that collapse. And if you're not providing intimate contact and you need to collapse here, but the other unwelded part's holding it up, that's no good. You have to collapse both. And you can do that either with the scanner bouncing back and forth, or do one all the way and the second one all the way. It kind of depends on how fast we can get up to temp.
Okay, so this is great. Do parts need to be flat, or can the laser focus and defocus per the contour? So there's 2D scanners and 3D scanners. 2D scanners is what you typically use with quasi-simultaneous. A 3D scanner is not quite as fast. Yes?
Yeah, that's right. It's not as fast, but it will adjust the focus. It adds a premium to the machine, but it's, in some cases, you need it. And essentially just, that scanner allows for the focus to happen while the contour is happening, right? So definitely doable. Mm-hmm. I don't think it's as necessary as what people might think. If you've got a little bit of rise, maybe you can use a mirror. Maybe you need a second laser source and scanner. But I would say it's a pretty advanced application, and we'd love to work through those options with you.
Mm-hmm. We are not exhibiting at PTXPO next month.
Maybe we should.
Maybe we should. We should look into that. Is there a maximum part size that is compatible with laser welding?
We have. We've looked at 52-inch long parts with contour welding. I'll honestly say we haven't done those. We haven't done those machines. We have done multiple scanners for, I'd say, 24-inch wide parts. Mm-hmm. But sky's the limit. And I think, as you kind of saw through Jason bringing this up right now, what does the application require? I mean, that's what it's all about.
Mm-hmm. Yep.
Cylindrical parts, absolutely. There's mirrors. Jason's showing, definitely an option. You don't have to use mirrors. You can rotate them apart. We just find that it gives you more flexibility. If you have multiple part numbers, you can change tools at a much more cost-effective way rather than moving the laser. Is there a difference in terms of sealing compared to ultrasonic welding? I would say no. No, great question. Great question.
Is it possible to control both press in force and weld depth simultaneously, or would it be either or?
Good question. I would say it's either or. No, actually, I would say our recommendation is typically to weld to collapse, and we vary the force to make sure we have the intimate contact. It's definitely a control parameter, but it's not the driving parameter. The number one parameter that's driving the process for us is weld collapse. Mm-hmm. You can adjust that force. You can see there we've got those 3 different options. Settling speed is a little bit down in the weeds, but it's essentially how pliable is that material. And so, it sort of settles in a little bit, and then we start the weld process. So it allows us to do a little bit of a delay to make sure we've got the intimate contact before we start the welding process.
If you had a 45-degree angle over a 1-inch section and then the rest of it was flat, would you need a 3D scanner?
Austin's got a pretty specific question there. I would say 45 degrees is a bit dicey because you can refract off of it. The angle of incidence is going to be a potential concern on that. We could get the focus there, but we would just need to be cautious with that. And I might say that would probably be a case where we want to look at either using a mirror to try to get, from the side, hit at a different angle, which we would just optically engineer that, make sure we've got the right position, or maybe another scanner. That sounds like a tough one. Great question, though. Laser staking in addition to adhesives.
Laser staking?
Well, I would say we've looked at laser, or like curing with laser. So if you've got like an epoxy, different than adhesive, that could be an option. Yeah, staking. We typically refer to staking as riveting, which is a mechanical adhesion, is a mechanical joining process. And we've not. It's just, the cost benefit just doesn't seem to do that. And you should definitely check out our InfraStake and NanoStake product if you've got some staking applications.
So if you guys are, you can keep answering questions. I'm going to put a link in the chat. If you want us to come to your facility and do training with your team on laser plastic welding, infrared welding, plastic staking, hot plate weld, any of these different plastic joining technologies, I'm going to put the list up. It's these. We do these all the time. And if you'd like us to come in and provide training for your team and do a very interactive and engaging session, just like we did today, but on site,
About your applications.
Yes.
I would say we can get obviously very specific and work through details that obviously we're not going to do with a broad group like this.
We often will come in, do the training for the whole team, and then have meetings scheduled with various individuals afterwards to review specific applications. And we really welcome that. And so if you want us to come in and do that, you can just drop that in the chat and say, hey, I would love you guys to come and do training at our facility. Yes, we will be sharing the slides and as well as the recording of this webinar. Should be coming to you via email a little bit later today. So I've had a chance to polish it all up and cut out all the mistakes we made. We made any mistakes. If we didn't answer your question, we apologize because there was a lot of questions. We did our best. But we will be following up with all of you via email, and you can ask your question again then. We'd be happy to have a separate call with you or your team. And I hope you guys all have a great rest of your day. Thanks for joining.
Thanks, everybody.